The first presentation is 3D image processing from capture to display by Dr. Toshiaki Fujii. So if you are ready, please.
Thank you. Can you hear me? Okay. Okay, thank you very much for your kind introduction. I'm Fujii from Nagoya University, Japan. And first of all, I'd like to say congratulations 30th year of this SD&A. And the other day, Professor Uz contacted me to present my work in this very anniversary. And it was a good chance to look back my history. And this is a list of the papers I presented here in this conference. The first one is 1994, when I was a student of Tokyo University. Data compression of orthoscopic 3D image. And this is the very first one. And then the highlighted red one is the papers presented in this conference. The others are SPI, for example, ITCOM or other VSIP, any other conference. And this is the second page, then this is the third page. And this is the final one. It's today's talk. Thank you. Okay, thank you very much. This is the 45th presentation. Thank you very much. And today's talk is a 3D communication system from capture to display. And at that time, I mean 1994, when I was a student, I was thinking this kind of 3D communication system. The 3D capture by a 3D camera, and compression coding here, and the 3D display. This kind of communication system, at that time, we are thinking of. But after that, this is from the figure from my doctor's thesis. At that time, there are many input systems for 3D, and many various output systems for 3D. And what should the transmission or coding should be in this kind of various input and various output case. So at that time, I discussed with my supervisor, and it should be like this. Any kind of 3D input is converted to common data format. And then at the decoder side, common data format is again converted to various types of 3D display. So from this context, we propose this ray space representation. Ray space is defined like this. This is 3D space XYZ, and this is 3D object, and light ray emitted from this object is parameterized. This is the z equals 0 plane, and this is the intersection point x and y. And incident, light ray, it goes through this point and then goes to this direction, theta and phi. And if we define intensity f of this light ray, we can define this ray space data f, x, y, theta, phi. So using this 4D data, we can reconstruct any kind of 3D information. This is my PhD thesis, first published 1994 and 1995. And this concept is very similar to very famous light field. Light field is proposed by Professor Levoy in 1996 in SIGGRAPH. That these two concepts are completely the same, mathematically same, but the parameterization is a little different. Okay. And this is from 2011 IEEE Signal Processing magazine. We introduced this kind of ray space, and this is a 3D case of ray space, x, y, and theta, tangent theta in this case. And if we cut this volume in section 1, for example, we can get this kind of view image. If we cut this 3D volume in this section 2, we can get this kind of view images. So any viewpoint, free viewpoint image is included this ray space 3D data. This is orthogonal case, this is spherical case. And this is from IEEE Signal Processing Magazine, 2007. So multi-view imaging, 3D TV. He's watching ray space here. Okay, yes, okay, it was introduced here. And so this is the first point. I started the 3D image processing in 1994, but it is not correct. This should be like this. Ray space is captured and processed, transmitted, and then displayed. This ray space communication or light field communication is essential communication. So in this context, we proposed this kind of free viewpoint TV system based on ray space representation in 2002. So 3D scene is captured or through some interpolation or some processing and captured. And then ray space coding or image processing, ray space processing is conducted and then displayed on any kind of 3D display. So today I'd like to talk about one by one, but because of time, I'd like to focus on this acquisition part today. And this is the acquisition system. So there are here 4 kinds of acquisition system. First one is multi-camera system, and the second one is space division multiplexing. Third one is time division multiplexing. Then finally, computational photography. I'd like to introduce these 4 techniques one by one. The first one is the multi-camera system, and excuse me. Yes. The first one is multi-camera system. In this case, we have 8 cameras, 4x4 cameras. And at that time means 2004, 5, 6, there are many camera system proposed. This figure shows high-performance imaging using large camera arrays proposed by Dr. Will Byrne of Stanford University. They developed over 100 camera systems. Similarly, Carnegie Mellon University developed this kind of multi-camera system. And we, Nagoya University, developed 100 camera systems between 2002 and 2007. This is which we proposed it in ICM in 2006. We developed 100 camera this system like this, 100 to 1 line, and 20 camera 5 loads, the 100 camera system. The specification is like this. The resolution is not so high, but at that time it was very high. And no compression was conducted, and the synchronization is less than 1 microsecond. This is very precise synchronization. And the camera is like this, and 100 cameras. This is the arc arrangement of 100 camera and 2D rows, 20 by 5 rows, 100 camera. And we captured various kinds of scenes using 100 camera system. And we provided these sequences to MPEG, you know MPEG, video and audio standardization meetings, MPEG. And this is one example. So this is very well known. You know, movie Matrix, but this is before Matrix was opened. And this is some other test sequence provided to MPEG. This is called Champagne Tower sequence. But we captured in our laboratory this sequence. But the champagne is very expensive, so we used Japanese green tea. Okay. This is an MPEG sequence captured in studio. So it was very mess. 100 camera system, very, very hard task for us. And calibration is also very important, and we used post-it card to align camera orientation or positions. So the second one is space division multiplexing. Maybe this is the next Kawakita-san, Dr. Kawakita will give a presentation about this integral photography developed by NHK, or light field camera. This is very famous word now, light field camera. Maybe emerged about 2005 or around 2005 or 2006. And the principle is like this. Place the micro lens array just behind, in front of image sensor, and capture a multi-view image like this. Okay, this is micro lens array, the imager. This is called space division multiplexing. The next one is time division multiplexing. Instead of arranging 100 camera, use just one camera, but moving. But this is very, of course, it is very difficult. So we developed special optics. So the object is here, and the two parabolic mirrors are set here. And then this object's real image is located here. This is object pig, and then we can put gravimeter mirror here and capture this image using high-speed camera. Oh, this is not working. Okay, the final one is computational photography. This is very recent work. Instead of using multiple cameras, we used aperture or mask, coded aperture or coded mask. And we can capture this kind of multi-view images using coded aperture. This is a case where we open just one aperture and the rest is closed. But instead of capturing one by one capture, we can capture this using this kind of mask and this kind of multiple images. And reconstruction is some kind of, we used this mathematical formulation, compressed sensing. Solving this to minimize this objective function, we can get this sparse vector theta. And once we get this theta, we can reconstruct multi-view images. So, but this computation is very heavy, so we used this computation. We replaced this computation with deep neural network, in this case, the autoencoder, and we constructed this kind of deep neural network architecture, and input is 25 light field images, and acquired images just 2. So we capture just 2 multiplexed images and then reconstruct 25 light field array space data here. And this is results. Ours is the best in this case. This is ground truth, and our case is like this. And using CNS, we can get very high-speed computation here. Okay, so finally, I'd like to show this kind of full FTV system from capture to display. And we reconstructed multi-view image capture and real-time display system. Okay, this is captured images. Okay. Thank you. This is captured images using 16 cameras. And we processed these video images, and then we reconstruct this continuous image. So we can go into the aquarium scene. Okay, this is not just enlargement. We can go through the scene. And this is the 360 time multiplexing capturing and 360 display demo. This 360 time multiplexing capturing camera, and this is 360 degree display. This is real-time capturing and real-time display. No compression is conducted. This display was developed by Endo sensei from Nagoya University of Technology. And finally, I'd like to introduce this multi-camera capture and layer display system. The using multiple camera, multiple view is captured and then transmitted and then calculate the 3 layers and display. This is a very heavy computation is required. The multi-view image is using a multi-view image. We have to calculate these 3 layer patterns, and this is also replaced by DNN or CNN in this case. And the similar network, we can reconstruct 25 image, multi-view images. This is the result. So multiple view image is captured and using coded aperture camera and converted to the 3 layers, and 25 images reconstructed using CNN. This is experimental results. This kind of 3D image was reconstructed using coded aperture camera and 3-layer display. Okay, so today my talk was focused on this light field or ray space capturing, processing, and display images. This is the whole system, and we introduced some kind of this acquisition, processing, and display. So this is acknowledgement to all our lab members. Then thank you for your attention.